This conference will now be recorded.
So very good evening, students. Today we'll be discussing very important topics of the semiconductor physics, that is intrinsic and extrinsic semiconductor and p-type, n-type semiconductor. How do you get those after doping? And if time permits, we will start with p-n junction. So let us first know what is intrinsic semiconductor. So intrinsic semiconductor is actually a pure semiconductor. Pure semiconductor is called intrinsic one. Okay, intrinsic semiconductor. Okay, so what is pure semiconductor or intrinsic semiconductor? We'll learn the physics behind this in detail, and for that we'll take two elemental semiconductors, silicon and germanium, and try to understand what is extrinsic and what is intrinsic semiconductor, taking these two elemental semiconductors, silicon and germanium. Okay, so this silicon and germanium, they have a special crystal structure, very special crystal structure. Even carbon also has the same, that is a diamond structure. You have diamond structure like this. Okay, so diamond structure. What does this diamond structure actually mean? Each side or each atom will have four nearest neighbor. Okay, four nearest neighbor. So that is the specialty of diamond structure. So in three-dimensional view, this is the crystal structure of silicon, germanium, or carbon. All these three has the same crystal structure, that is diamond structure. I have told diamond structure means there are four nearest neighbor, four nearest neighbor in each direction. If you take in any direction, like any atom you take, it will have four nearest neighbor, and that thing has been depicted in two dimension or in planar structure. This is the schematic of this three-dimensional structure. What I am saying is that there are four nearest neighbor. That is the specialty of diamond structure. So this is the three-dimensional view, and this is simplified two-dimensional schematic. Two-dimensional schematic or a planar view of diamond structure. This is a planar view of diamond structure. You can see silicon and germanium we have discussed in the previous class. They have actually four valence electron. Four valence electron. That means in the outermost orbit, they have four electrons. Okay, four electrons. Both silicon and germanium. They have four electrons, valence electron. And see, in the crystal structure, in the three-dimensional crystal structure, generally, what do you mean by crystal? Actually, in the crystal, there will be innumerable or a very large number of atoms, very large number of atoms like silicon or germanium, and they will be arranged in a particular manner, particular periodic manner. So if I say this is the silicon atom, then there will be a periodicity they maintain in the structure. Like that, they may be arranged. Okay, all these are silicon or germanium. So they have a particular periodicity to occur in the crystal. So what I'm trying to say is that if this is the planar view, you look here. These are all silicon atoms or germanium if you take, then it is all the germanium atoms are arranged with a particular periodicity maintained in the structure. Crystal structure means there is a definite periodicity maintaining inside by the atoms. Okay. All right. So this is a typical germanium or silicon crystal in two-dimensional plane. Okay. This is the planar view. If you think this is a silicon, these are all silicons there. And you look this one atom, if you consider this particular atom, since it is having a four valence electron, suppose you have this is nucleus. Okay, let me in this notation, what you see in this figure, the silicon atom or germanium atom has been written as +4. Why is it so? Because if you have a nucleus and you have all the orbits, so in the outermost orbit you have four electrons, right? Four electrons in the outermost orbit. If these four electrons are almost separated from this particular nucleus or the core, okay, so what you get is effectively positive. If these electrons go away, then this nucleus will have effectively positive charge, and that is four positive charges. So effectively four positive charges will be added to the nucleus. So if you leave the four valence electrons, then the four electrons along with the nucleus is written as +4. So that's why it is +4 silicon or germanium atom. And see, these are the valence electrons. This is 1, then 2, then 3, 4. These are the four valence electrons which are associated with this particular atom. So Now see, I'm saying the diamond structure has a specialty that it has four nearest neighbors. So this is the original silicon atom, suppose, which I am considering. So it has four nearest neighbor. Look, these are the four nearest neighbor. This is actually diamond structure. This is the schematic in two dimensions. But this is the same thing you can see in the any direction. Okay, so this is the germanium or silicon. Now look what happens. Since each of this silicon contains four valence electrons and they have four nearest neighbors, then what will happen? This particular atom will share four of its electrons with four nearest neighbors. Okay, four nearest neighbors. Suppose this is the electron. Electron from this, it will share with this particular nearest neighbor. So this electron will be shared with this, and this electron will be shared with this atom, and another electron, this one will be shared with this. At the same time, the nearest neighbors also, they will share their one, like this will be shared with this atom, and this is the nearest neighbor. So this has electron, this one, this will be shared with it. So actually they do mutually this do share their valence electrons with neighboring atoms. Okay, and thus by sharing they can actually access these two electrons for their completeness of the octet. Okay, anyway, so these electrons are shared by these two nearest neighbor. Again, these two electrons are shared by each other. These two electrons are shared by each other. These electrons actually circle back and forth between these two host atoms, and thus they make a strong covalent bond. They make a covalent bond with nearest neighbor. So this will make with this. Again, this will make with this. Like that, you can see this as a covalent bond. They are making with each other. So how do they make covalent bond? So each nearest neighbor will share their valence electron to its nearest neighbors, like with the nearest neighbor, and use those electrons for their purpose. Okay, and thus they make a strong relationship or strong covalent bond between them. Okay, you can see the dotted lines. These are all covalent bonds. Okay, these are covalent bonds. So this is a covalent bond between these two. This is a covalent bond between these two atoms. This is covalent bond between these two atoms, like that. So you can see in this structure, the covalent bonds are formed with, between the silicon atoms or germanium atoms. Okay, and that is fine. So far, what we have learned that they will. So all the valence electrons will be actually bound by the covalent bond. Or in other words, the covalent bonds are created by sharing their electrons with neighbors, and thus the crystal will be a very compact and it will be strong. It will have a strong lattice structure. Okay. Now in this, you look, intrinsic semiconductor will say pure semiconductor. So this is a pure semiconductor like silicon or germanium. And when pure silicon or pure germanium is taken, then this is how we'll get strong covalent bond. And you look, by sharing this bond, covalent bond, each of them will actually complete their octet. And thus, there will be no free charges to conduct electricity. There are no free charges, so all the bonds are contact, like intact at 0 Kelvin temperature or absolute zero temperature. All these bonds will be very much intact, and electrons will be actually shared by the host atoms. Okay, so covalent bond will be very strong and intact at absolute zero temperature. But if you increase the temperature of this particular lattice even slightly greater than this 0 Kelvin temperature, or maybe uh, slightly greater than room temperature or nearly at room temperature, these bonds will not be intact. So we have learned what is called, like, what is diamond structure, and we have already seen that silicons or germanium, they have a very intact, very good covalent bonds among the atoms, and these bonds will be very much intact at low temperature. At absolute zero temperature, each and every bond will be very much strong to bound the nearby atoms. Okay. Now, if you slightly raise the temperature of this pure semiconductor, pure silicon or germanium, if you slightly increase the temperature, then what happens? These bonds will no longer be intact. There will be a tendency to break some, like any of the covalent bond, and set some of the electrons free to move around the crystal. I'll repeat. I may have figured. You look here. Look this. So we have seen for pure semiconductor at very low temperature, the bonds are all very intact, and there will be no free charges for conducting electricity. That is the point over here. But if the temperature is raised little bit, even at room temperature also, or slightly greater than room temperature, what happens? These bonds will not be intact because of the thermal energy or thermal excitation. Some of the bonds will be broken. Some of the bonds will be broken. As you see here, there will be a breakage of the bond here. Okay, one bond is broken, and that particular electron which was involved in this bond making, that will be freed from this bonding, and that will become a conduction electron. That becomes a conduction electron and free to rotate, free to move anywhere and everywhere. Free to move anywhere and everywhere in this lattice. That is called free electron. So these electrons are called thermally generated free electrons. Thermally generated free electrons. So what we get, that if the temperature is raised slightly, even slightly greater than room temperature or even at room temperature, there will be breakage of some bonds, and hence electrons will be freed. And those electrons are called free electrons because they can move anywhere in the lattice. If you apply a certain electric field, that will move in a particular direction, giving rise to some current. Okay, so those electrons are called thermally generated electrons, and they behave as conduction electrons. Okay, fine. So electrons are formed, bonds are broken. That means electron has been freed from that particular bond. But what happens at that position from where the electron has been freed from? Okay, so that position will be vacant. If suppose there was a chair and somebody was sitting, if we just leave the chair, then this chair will be vacant. Similarly, see in the bond, you look, there was a bond which is now broken in the sense the electron has left that particular bond because of the excitation of the thermal energy. It is not able to sit over here freely, or yeah. So then that electron will be freed from this bond. Now at this place, since the electron has negative charge, since the electron has left that particular position, then it is assumed that that particular position there will be equivalent amount of positive charges. Equivalent amount of positive charges will be there. Okay, equivalent amount of positive charges may be there at that particular position. So this is called hole. See, this is empty circle. This is called hole. So hole means vacancy of electrons. What do you mean by holes? Absence of electron is called holes, because from this bond the electron has left or become free. Then this particular position will be, or this side, this is called a side, atomic side. So this particular side will be vacant. Yeah. So this particular side will be vacant, and there will be absence of electron. Absence of electron means increase in or gain in positive charges. So since the electron is moving from here somewhere, then this particular position will be developing a effective positive charge, and this is called actually hole. This is called hole. Electrons and holes. So you can see when we apply some temperature or increase temperature, the thermally generated electron is produced. At the same time, there will be the production of thermally generated holes at the side of the electron. From where the electron is left, the hole will be created over there. Okay? And this hole also has a positive, equivalent positive charges of the electron. That's why in this semiconductor, holes and electrons, these are the charge carriers, hole and electrons. Not only electrons, not only holes. Holes and electrons both will be the charge carriers which will be conducting electricity. Okay, that's why in semiconductor it's very great, because there are two types of charge carriers, holes and electrons. Alright, so this is the thing, when just an electron is leaving a particular bond, breaking the bond, there will be a holes created. There will be a hole created at the side. This is called actually, suppose this is called side 1. Now this vacant position or absence of electron will not like to be like this. Nobody wants to be vacant. Okay? No places want to be vacant inside the crystal. So since there is no electron over here, so some electron from any neighboring atom will try to jump over here. Look here. So this is the side 1 and this is the side 2. Suppose the electron from side 2 has just moved here at side 1. Okay. Then what I'm trying to say is that the structure does not like to have a hole. So then what will happen? The electron from neighboring atom will jump over there. Okay. So this side now it is not in vacant, but there is no vacancy. But since the electron has left from here to fill up this vacancy, so there will be vacancy created over here at the side 2. Okay. Therefore, you look, these electrons which are created and the holes, these holes and electrons, they are actually moving in the opposite direction. And you look, this hole actually moved from side 1 to side 2, whereas electron moved from side 2 to side 1. Okay. So because of this, there will be two kinds of currents. One is called electronic current, another one is called hole current. Okay, that will learn Understood? So what we have learned? We have learned that how holes are created and electrons are created due to thermal excitation, and how electron and hole both can participate in the conduction process, because hole also will be moving. Actually, movement of or motion of hole, we know this. The electrons which are freed, those are already free electrons. They are not involved with the motion of the holes. So motion of holes can be interpreted as the motion of the bound electron. Motion of the bound electron. So why I'm saying that the motion of the hole means motion of bound electron, because there is a hole over side to 1 and some bound electron, these from side 2 will move here to fill up these vacancies, but leaving a vacancy, real vacancy over here. So this movement will give rise to some current, that is hole current, that is IH. Okay. All right. So the motion of holes can be interpreted as the motion of bound electrons. So this is so this is when with increase the temperature, some of the bond is broken, and then charge carriers holes and electrons will be created. So that's much we have learned. So not only generation of electrons and holes, there will be recombination also. Recombination. Okay, so recombination. There is something called recombination. Okay. So we have seen generation of electron, and now we see recombination of charge carriers. So recombination means what? See, this is hole and this is electron. Okay. Recombination means, suppose this is electron, this is field circle. Generally, with field circles will mean electron, and empty circle means holes. Okay. Now, as the electrons and these holes are created, at the same time, the recombination also happens. That means hole and electrons, they come very closer, and then these holes and electrons will be actually disappearing. Okay, disappearing in the sense they will be recombined. They will recombine to form their original state. Okay, so we have seen generation and recombination. Recombination means when a hole and electron they come in contact, their existence will not be there as individual hole and electron. Okay, they will have something, but they will see electron and hole will not be further separate entity when they come in contact to each other. That is called recombination. Like generation here, electrons and holes are generated by thermal excitation, and recombination also happens at the same time. Whenever there is generation, whenever there is generation of electrons by thermal excitation or some other way, there will be same number of holes created in the lattice. Okay, same number of holes generation of electrons and holes happens at the same time, recombination also will happen because you have electrons and holes in the lattice. But there will be some possibilities to come together or nearby, and then they recombine to form something, some entity, which will actually make this hole and electron to disappear. That is called recombination process. And recombination, rate of recombination and rate of generation of the charge carrier would be the same. So rate of generation and rate of recombination, forward process and backward process, both are actually having the same rate. So this is about intrinsic semiconductor. So in the intrinsic semiconductor, we are seeing the charge carriers, holes and electrons. They are having same concentration. They are having same concentration because they are created by thermal excitation at the same time. The number of electrons and the number of holes would be the same. That's why NE means number of concentration of electrons, and this is the concentration of holes. Okay, NE is the concentration of electrons, and NH is the concentration of hole. And at equilibrium or for intrinsic semiconductor, this NE is equal to NH. These are both equal. Okay, and because of the movement of the valence electron, we will have some current that is called electronic current. Electronic current, current obtained due to electronic motion, electronic current. And there will be current due to the motion of holes, that is called hole current.
Ram, voice is not good, Ram.
Oh, voice is not there.
Hey, yeah, you speak right now?
Yes. What about now? Is it there now? What about now, madam? Can you just respond to me?
Now it's okay, Ram. Previously, some dragging.
So how long? Okay, so how long it was not there? Then I'll repeat some of the sentences.
I went to take injection just 10 minutes. Previously, it was good.
Okay, so 10 minutes there is no sound, huh? Okay, I don't know how long it was not there. That's why if somebody is there, it is easy for me to understand. Anyway, I'll repeat some of the sentences in gist. Just a minute, madam.
Deepa also is not there.
Okay, so I'll just recap. Yeah, that's fine. So I'll just recap what I have discussed
Okay.
in short, so that if there is sound problem, student will not have any problem. I'll recap here what I have discussed.
Okay.
So in the intrinsic semiconductor, we have seen if we increase the temperature, then there will be thermally generated electrons and holes. We have already discussed how electrons are created. Electrons are created just by breaking of bonds. Some of the bonds will be broken, and electrons will be totally freed from the host or from the bond, and they can behave as free electron and giving rise to current that is called electronic current. By the motion of the free electron, we get IE, that is electronic current. Electronic current. Okay. All right. So now holes are created, and holes also will move How holes will move, that is shown here. The holes created in this site of 1 will not like to become like, see, hole means what? Absence of electrons. Absence of electrons is hole. Okay, and that has, if we take that absence of electron as a quantity, and that is denoted by just empty circle, and it has, since electrons has left this place, there will be equivalent effective positive charges. Okay, effective positive charge. So holes are actually just opposite to electrons. Electrons has negative charges and holes have positive charges. But one difference is that the holes are not free from the lattice. They cannot move freely as electron can do. Okay. The motion of electrons will be, sorry, motion of holes will be just interpreted as the motion of bound electron. How it is shown over here. So the site which is vacant over here, that site will try, like, that site will not remain always vacant. It will like to get some electron from the neighbor. So suppose this is the neighbor atom which will supply an electron, or electron from this neighbor atom will jump to this site, vacant site, to fill these vacancies. See, the site 1 was vacant. Now the electron from here has left or jumped over here in the site 1 to fill up this vacancy, and therefore this vacancy is now filled with electron, but vacancy will be created here. So therefore you can see that vacancy is moving from site 1 to site 2, and the bound electron moves from site 2 to site 1. Okay, so this is how holes will be actually moving, but within the lattice itself. Okay, so these are not free as electrons. Okay, so but in case of intrinsic semiconductor, the concentration means number density of electron per unit volume. Number of electrons per unit volume. This is electronic concentration, and NH is called whole concentration. Whole concentration, and this is electron concentration. Electronic concentration or electrons concentration. Okay, so electronic concentration. And for intrinsic case, you look, the electrons and holes are created at the same time. That means as many electrons are created, those many holes are also created. So therefore for intrinsic semiconductor, Ne is equal to Nh, and therefore the hole current and electronic current also will be equal. Okay, all right. Now one more important thing we will discuss, that is this is actually generation of electrons and holes, and we have discussed already recombination of holes and electrons. So what happens? See, from a bond, electrons and holes are created. Okay, holes and electrons are created because this hole has positive charge and electrons has negative charge. When they come in contact to each other, they will create a neutral entity. That means you will lose electrons and holes in summary. Okay, so you will actually lose one electron and one hole if they come close to each other or in contact to each other. Then they will create a neutral entity just losing one electron and one hole. This is called recombination process. Recombination, generation and recombination. This is electron and hole generation. Here it is happening electron and hole recombination. Okay. So at equilibrium, this rate of generation and recombination of charge recombination carriers are same. Okay, same. That means if there are 10 electrons and holes created per second, there is a possibility of recombination of 10 electrons per second. At equilibrium, rate of generation and rate of recombination is the same. Okay, so this much we have already discussed. We'll go to this particular portion. You look the band structure, energy band structure of intrinsic semiconductor. Look, this figure A is at 0 Kelvin temperature. That means at absolute zero temperature. As we have seen, at absolute zero temperature, all the bonds will be very, very intact to each other, and hence there will be no holes, no electrons generated for conduction. So this is conduction band. It is actually totally empty. You can see that empty at 0 Kelvin temperature, and this is completely filled with electrons. Okay, but if you increase the temperature, you look, some of the electrons from valence band can gain sufficient energy to overcome this band gap and go to the conduction band, leaving some vacancies or holes in the valence band. You look, these are the valence holes which are in the valence band, and these are the electrons which are in the conduction band. So you look, when temperature increases, what happens? Some of the electrons from valence band can go to conduction band, and then those electrons will be taking part in the conduction process. That's why as you increase the temperature, resistance decreases. So this is the reason, because more and more charge carriers will be created for conduction process. Okay, which will take part in the conduction process. So this is why as you increase the temperature, there will be decrease in the resistance in case of semiconductor. Okay, so these are the band structure we have discussed. Now, so these are two band structures, energy band diagrams, one for the intrinsic semiconductor at 0 Kelvin, and another one is actually representing the intrinsic semiconductor at any temperature greater than absolute zero temperature. Okay, now we'll go to the extrinsic part, which is another topic to be discussed today. So we have learned intrinsic, now extrinsic. What is extrinsic? That is impurity. Extrinsic semiconductor means impurity semiconductor. Okay, impurity semiconductor. I'll say why it is. Extrinsic, we have seen, we have elemental silicon or germanium. Okay, now we have seen that at very low temperature there is no conduction electrons, so there will be no conduction by semiconductor at low temperature or maybe at room temperature. Only when temperature increases, then significant amount of charge carriers are created at very, very high temperature, and then conduction happens. Okay, by intrinsic semiconductor. So since the carrier concentration in intrinsic semiconductor is very less, and hence conduction or conductivity is also very less. That's why with intrinsic semiconductor it is not useful to make any electronic device for practical purpose, because they have less carrier concentration. If there is less carrier concentration, then less or low conductivity. Low conductivity. Okay. So it is not useful to make devices out of intrinsic semiconductor. Therefore, there is a necessity to manipulate the pure semiconductor by doping or by mixing desirable impurities such that you can increase the carrier concentration inside the intrinsic semiconductor. Okay, if you increase the carrier concentration somehow, then the conductivity will be more. Okay, so that is what is done in case of extrinsic semiconductor or impurity semiconductor. A desirable impurity is mixed with the pure semiconductor silicon or germanium to increase the conductivity or increase the number of concentration of the carrier concentration of the carrier concentration in the intrinsic semiconductor. So impurity is added to increase the carrier concentration so that you get more conductivity, and with those practically useful device can be manufactured. Okay, all right, we'll see. Suppose this is a crystal structure. You can see two-dimensional structure, planar structure we have seen for silicon or germanium. So these are all +4, +4, +4. You look, this is +5. That means this is foreign element. This is not from its own. This is some other element. Okay. So this is desirable impurity which is added for increasing the concentration of electrons and holes. Okay. In some cases holes, some cases electrons. So we have seen silicon or germanium, they have 4 valence electrons. 4 valence electrons, and hence both are actually in the group 4. In the periodic table they are in the group 4. Okay, both have 4 valence electron, so they are in the group, these are actually group 4 elements. Okay, group 4. So group 4 elements, they have to be added with some impurity. So see, we cannot use any impurity. We like to increase the carrier concentration. Okay, we have to understand the science behind it, how to add impurity to this pure semiconductors, silicon and germanium. So as we have discussed, we need to mix with desirable impurity, not anything you like, desirable impurity. So how do you understand which are desirable impurities for what semiconductor, elemental semiconductor? Suppose in this case silicon and germanium. So first of all, let me tell you the process of adding desirable impurity to a certain intrinsic semiconductor to increase the carrier concentration or conductivity. That process is called doping. The process of mixing desirable impurity, that process, that is called doping, and the element you use to dope, or the element you dope, is called dopant. So these are two definitions you should remember, what is called doping and dopant. Doping and dopant, these are like the element which we mix, and the process of mixing is called doping. It is not simply called mixing, because mixing and doping is different. Okay, we'll discuss the differences. What is doping or mixing? Sorry, doping. Doping is that we choose some dopant in such a way that the ready in the sense, the size of the dopant and the electronic structure, or the valence electron, number of valence electrons, will be nearby, will have nearby value of this 4. I mean to say, if I have 4 valent tetravalent electron silicon and germanium, these are group 4 element, then I can take group 3 and group 4 element to dope with group 4, sorry, group 5 and group 3. These are the dopant which I can take to dope with the tetravalent host or intrinsic semiconductor. Excuse me, just a minute. Because these are the nearby groups, like nearby elements which may have almost similar ionic radii of tetravalent silicon and germanium, and they have valence electron 3 and 5, so these are nearby. So what is doping? As you mix either group 3 element or group 5 elements, a very little amount, 1 parts per million, so ppm parts per million to this, then what happens? These elements, like atoms, these impurity atoms will just go and sit at the lattice site of the silicon or germanium. Just by knocking one atom or more than one atom, they will sit at the lattice site of the silicon itself. They will not disturb the structure. They will not disturb the structure. They will not sit anywhere they like. They will not sit here and there or here. They will sit at the particular site of the silicon. They will just knock out some silicon atom and sit at their sites. So this is the process of doping, and what happens is this. What happens upon doping? The dopant atom or ions will just knock out silicon atoms and sit over their sides, okay, such that the structure of the lattice structure of the semiconductor, intrinsic semiconductor, does not change upon doping. Okay, now look, this is, so there are, as I said, there are trivalent impurities which we can dope with, or dopants are there. There are two types of dopants. I have already discussed dopants. One is trivalent like boron, indium, aluminium, etc. So trivalent, boron, aluminium, then indium. These are the trivalent, some of the trivalent impurities which we can use a dopant. Okay, and we can use pentavalent, pentavalent, pentavalent like arsenic, antimony, phosphorus, etc. Okay, so these are some pentavalent dopant. Now we'll see, when we dope this tetravalent silicon or germanium with trivalent and pentavalent dopant, completely different semiconductor is being obtained. Oh my God. Madam, are you there? Is it still audible or there is some problem? Deepa, I think Deepa is there. Can you confirm me whether it is audible or there is some issue with the sound? I hope you are able to listen. Okay. Deepa, you can write to me in the message box whether you are able to hear me. I hope you are able to hear me. I'll continue then. So there are two types of dopants as I was discussing. So there are trivalent and pentavalent. So trivalent and pentavalent. Now we'll discuss upon doping with trivalent and pentavalent impurities. We'll get different types of semiconductors. One is p-type semiconductor, another one is n-type semiconductor. Now we'll see n-type semiconductor. N-type semiconductor. Okay, n-type semiconductors. So how do we get n-type semiconductor? If we dope silicon or germanium with pentavalent impurities like arsenic, phosphorus, antimony, these dopants. Okay, if we dope with such pentavalent dopant, then what happens? As I discussed, they will actually, some of the dopant atoms will knock out silicon or germanium atoms and they will occupy their side. See, this is the figure, representative figure, that one pentavalent atom is sitting over here. Pentavalent atom means it has, suppose this is the atom, it has 5 valence electron. Okay, 5 valence electron. And now if it has 5 valence, like 5 valence electrons, and it is in the side where it has 4 nearest neighbor. One is here, another one is here, here and here. So out of 5 valence electrons, 4 of them will take part in making covalent bond with the nearest neighbors. I hope you are understanding that the pentavalent dopant has 5 valence electron, and out of 5 valence electron, 4 of them, they will take part in the bonding process, covalent bond. And the other one, the fifth one, will be actually become loosely bound to the host atom, and that will be actually left buried, or that will be freed from the host pentavalent atom. Okay, you can see this is the unbound free electron which is obtained from the dopant atom, and it is actually, see, it is becoming completely free to move anywhere in the crystal structure. Therefore I can say this pentavalent impurity has donated this electron. Okay, so that's why this atom, pentavalent atom, is called donor atom or donor ion. So why I am writing here positive 5? Because you have 4 electrons, sorry, 5 valence electrons. 4 of them are taking part in the bonding process, and one will be leaving. That means when it is leaving one, or see 4 electrons, so this is the core, actually core, because 4 electrons are already engaged in making covalent bond, and another one is left. So effectively 5 positive charges will be added to the core. Excuse me. So that's why it is written as +5. And in case of this silicon, like, look, they have 4 electrons, all 4s are taking part in the bonding. That's why the core will be effectively positively charged by 4 unit. Okay, so this is how you look what we get upon doping with pentavalent atom, arsenic, antimony, or maybe phosphorus. What we get is that we get one positive donor core on a one positive donor core plus one electron. We get an electron, extra electron, which is free to move anywhere in the crystal structure and give rise to conduction current. So this is the situation when we dope intrinsic semiconductor with pentavalent dopant, you get an extra electron. See, for intrinsic case, thermally generated electrons are already there. So you have now total electrons, thermally generated electrons plus electrons donated by impurity dopant. Okay, impurity donated by impurity. That means you look, but the holes are not created by this impurity. Only electrons are created. Holes are only created by thermal generation. Okay, since see, if suppose I have 10 holes, intrinsically 10 electrons also will be there. Those are already there, and along with that maybe some 10 or maybe some 50 electrons are created by this doping. So the concentration of electrons is actually increasing. As I said, at the same time recombination also will happen. Since there are more electrons, upon recombination holes will be, see, 5, suppose 5 electrons just recombine 5 holes. That means actually effectively holes concentration will be decreasing. Upon recombination, the concentration of the holes will be decreasing only. Suppose I have 60 electrons now, okay, and you have 10 holes only. If recombination happens, 10 holes will be just recombine with 10 electrons. Still we will have 50 electrons extra. So you can get more and more conduction electron by this doping. Okay, that means we are increasing the carrier concentration here. The electrons are increased in this intrinsic semiconductor. Sorry, this is extrinsic semiconductor after doping. So in the extrinsic semiconductor you get more carrier concentration depending on the nature of the doping. If this is pentavalent doping, then we get more electrons. That's how what we can say here is that the concentration of electrons or electronic concentration will be much more than the whole concentration. So Ne will be much more than NH in this case. Okay, so concentration of the whole will be very less than the concentration, carrier concentration of the electrons. That's why it is, these electrons are called majority. Electrons are called majority. Here majority charge carriers, and these are called minority charge carriers, and such semiconductors are called N-type semiconductor because electronic charge carriers are majority in this type of semiconductor. When you dope a intrinsic, like an intrinsic silicon or germanium with pentavalent impurities, then negative charges or electronic charges become majority charge carriers, and hence it is called N-type semiconductor. N-type semiconductor. So the extrinsic semiconductor in which the electrons are majority in number are called N-type semiconductor. So in the N-type semiconductor, the carrier concentration of electron is more, and hence the electronic current will be more than hole current, but both the currents will be there in the semiconductor material. Okay, all right. Now we'll see if we dope with trivalent, then what happens. Trivalent means there are three valent electrons. As you see, this is one, this is one, this is one, and this is one. There are three. So they see three. This this is suppose boron or aluminum. So this atom will make covalent bond with three nearest neighbor. With this three, because I have now three valence electron, so it will create covalent bond with these nearest neighbors. Okay, so three nearest neighbor. But what about the other? So other also will be making a bond, but there will be no electron, there will be hole. Okay, so the other bond will be created by the holes, you can say. Okay, so you can see here, and in this case you look, this hole is created as you add the dopant like boron, or sorry, boron, aluminum, boron, indium, aluminum. Okay, if you use this kind of dopants, then they have three valence electron, and they will actually three valence electron will take part in the bonding process, making in covalent bond. But at the same time, it will make a covalent bond with the fourth one with a hole. Okay, hole in the sense there will be absence of electron in that particular bonding. Okay, and as we know, since it is actually releasing one electron, in fact it is, see, it is, this core is actually just accepting one electron. See what happens when this hole is actually taking part, in this case in the bonding process, one electron, because hole does not like to be vacant. So one electron from the nearest neighbor, suppose from here, just jump to this, and hence the the bonding will be complete over here. But this process will be dynamic. Dynamic means it will be sometime filled with electron, sometime it will be vacant, sometime filled with electron, sometime it will be vacant. Okay, this is what will happen. So when electron actually is added here, so you can see that effectively it will have one electronic charge or negative charge extra. So that's why the core, the core is actually given as a single, like minus sign over here. And why this is called core, acceptor core? Because it is accepting one electron, that's why it is called acceptor core. In previous case it was actually donating one electron, that's why that is called donor core. Donor core, because it was donating one electron and becoming effectively positively charged. In this case it is accepting one electron and becoming effectively negatively charged. Okay, so that's why this is called acceptor impurity, or acceptor ion core, or acceptor core simply. And this hole, we have already discussed how this moves. They will move according to uh, the previous process, like say one electron from the neighboring atom will jump here, then the hole will be moving from here to here. So this is how we have already discussed how hole moves. So in this case, since, so this is shown for only one dopant atom which is sitting in the site of silicon or germanium, knocking out one of them. But if there are Avogadro number of dopant atom which are just knocking out and sitting over there, so if we have many such dopant, trivalent dopant atom in the lattice, then we'll have more and more holes. So same example if I give earlier, there was intrinsically 10 holes. okay, and 10 electrons, 10 electrons, okay, 10 electrons suppose intrinsically. But now upon doping you increase some 50 holes, okay, maybe more than that, much more than that, 50 holes. Now recombination, due to recombination what happens, these electrons will be actually recombined with these holes, and 50 holes you will get. In the sense, the majority charge carriers in this case will be the holes which has positive effective charges. Okay, that's why it is called p-type semiconductor. P-type semiconductor. So what is p-type semiconductor? A extrinsic semiconductor which is doped with trivalent impurity will have the hole concentration much greater than an electronic concentration, okay, and hence the current also will be more here due to holes than electron, okay. So this is p-type semiconductor, and we'll see in case of p-type and n-type semiconductor what happens. Since there is a donor impurity, so there will be a donor level created just below the conduction level or conduction energy level, just below the conduction energy level EC. There will be ED, donor level created, and see this has excitation energy 0.01 electron volt. That means if some electrons are there in this donor level, they will be easily excited to conduction band just by applying this much energy, okay, this much energy. So this is the donor level. And what is the advantage of donor level? So if some electron somehow reaches here in the donor level from this valence band, then those electrons easily can move just by giving, just by thermal excitation. Even at room temperature, electrons from here, it can go directly to there, okay. So then the conduction process become easier again. And in this case, since this is the ED level and this is the valence band, so EG also decreases, okay, EG decreases, okay, EG decreases, band gap decreases, okay. Now if you dope with trivalent, then there will be acceptor level created just above the valence band, and you can see this is the energy difference between this valence band and this acceptor level. So electrons can anytime jump to or can move to this acceptor level upon thermally excited, becoming thermally excited. And here also see EC minus, now EG equal to EC minus EA, EC minus EA, EC minus EA. EA means acceptor level, energy of acceptor level. This is energy of conduction level, okay. So this is how, if somehow some electrons from valence band can reach to here, they may be excited to conduction band more easily than earlier, okay. So this is the band structure at temperature greater than 0 Kelvin for extrinsic semiconductors, okay. And this extrinsic semiconductor is, okay, so we have already learned what are called p-type and n-type semiconductors, and this is actually n-type semiconductor where donor level is n-type, this is n-type, and this is p-type semiconductor. Acceptable level is created, okay. So with this we'll stop it here for today. Since there was a sound issue, I had to recap and I took little extra time. So next day we'll learn how PN junction is created, and we'll learn PN junction diode and related physics in that class, okay. So I'll stop it here for today. We'll meet again on Wednesday. with PN junction, how PN junction is created, what are the underlying physics in the PN junction, and what is PN junction diode, etc. We'll be learning in the next class. Okay, so Deepa, if you have any quick doubt, you can ask me related to this P type, N type, or intrinsic, extrinsic semiconductor, etc. If you have any doubt, you can ask me now. Okay, so I hope you don't have any questions. So I'll stop it here. Bye for today.